Right, so we've been talking about pairs of random variables for a while, and we're ready to talk about an important family of two random variables. So we're going to introduce our first family of pairs of random variables, and it generalizes to n random variables, and this is jointly Gaussian random variables. And the reason that we're going to introduce this particular family is it does a very good job of capturing dependencies between random variables. Okay, and before we specify exactly what we mean by jointly Gaussian random variables, we're going to need some building blocks. Okay, so if I were to just write for you the joint PDF, it would be a bit confusing and you might not see through to the intuition right away. So we're going to build our way to this family with some smaller parts. Okay, so let's say that U and V are independent standard Gaussian random variables if they satisfy the following distribution. So U is Gaussian with mean 0 and variance 1. V is Gaussian with mean 0 and variance 1. And U and V are independent. Okay, so the independent part is clear and the standard part refers to the 0, 1 parameter choice. Then the joint PDF of these two random variables U and V is FUV, which is FU times FV. And I can just write that using independence, and that's 1 over square root 2 pi e to the minus u squared over 2 times 1 over square root 2 pi e to the minus v squared over 2. I can combine those two exponents and the square root of 2 pi, so I get 1 over 2 pi e to the minus u squared plus v squared over 2. Okay, so that's our joint PDF for independent standard Gaussian random variables. But what does that look like? So let's take a moment to visualize this joint PDF. Okay, so what I'm going to do is just take this function and do a 3D surface plot. So I'm going to just plot what this thing looks like, and it looks like a hill. Okay, so it's a hill centered at 0, 0, and it kind of smoothly rises up and then just goes back down. Still a little hard to see from this plot what's going on. So what I'm going to do is use some colors to denote amplitude. Okay, so I'm going to reproduce the same plot here. So this is a 3D surface plot now with color. And you can see that the highest values are in red, and then it goes down to orange, yellow, green, blue, all the way down to purple for 0. Okay, so this is a little bit easier to visualize what's going on. And now these 3D surface plots are kind of cool to look at, but they don't really capture the intuition we need because it's hard, again, to sort of see the whole thing from the 3D. So it's actually often useful to have a contour plot. And what is a contour plot? Well, it's just this heat map of the heights over the range. Okay, so you can see underneath this 3D surface plot, I've now drawn the contour plot. So I keep the colors and I just project them downward onto the UV plane. And so what I can do is just remove the surface plot and just look at this 2D plane, take a top-down view, and I'm going to get my contour plot. Okay, so this contour plot is what we're going to work with to build up our intuition. You can see that it's nice in the sense that I just have a circularly symmetric distribution. So it's kind of red in a circle, and then it kind of goes to a lower level. So this is this hill kind of falling off, and I can visualize this using this contour plot, okay, which bins these values in terms of different colors. Okay, well, now that I have this, I'm going to go and introduce this idea of jointly Gaussian random variables. So x and y are jointly Gaussian random variables if I can write them in a particular way. Okay, so what I need to be able to do is express them as linear combinations of some other random variables which happen to be independent standard Gaussians. Call them u and v. Okay, so I need to be able to write x as au plus bv plus mu x, and y as cu plus dv plus mu y. Okay, so it doesn't matter where u and v come from, so they just have to exist behind the scenes, but I need to be able to show that x and y can in fact be written as linear combinations of these independent Gaussians, plus some mean offsets. All right, and the idea is that depending on the parameters that I pick here, then the joint PDF of xy might be the following thing. So it could be shifted, so I could move it across. It could be stretched, or it could be both. Okay, so I have both. And this is all relative to the symmetric centered at 0 joint PDF of U and V. So if you remember, that one was a hill that was circularly symmetric. It was centered at 0, 0. And so when I shift it, I might move it to a different center. And when I stretch it, maybe I'm stretching one or both axes, or I could stretch it and shift it, right? And we're going to try to understand what is the role of each of these operations. Okay, well, now that we have a little bit of a picture of what this thing is going to look like, let's write out the joint PDF, and maybe you'll appreciate why I didn't want to do this first. So here's the joint PDF for jointly Gaussian x and y. So pair of random variables x and y are jointly Gaussian if their PDF has this form. And so I can write it as this normalization term. Okay, so there's this constant out front. So let me just read this to you. So it's 1 over 2 pi, the standard deviation of x times the standard deviation of y times the square root of 1 minus the correlation coefficient squared. Okay, so that's already a lot to take in, but that's just the normalization constant. The really interesting stuff is happening inside this exponent. It's got this constant, which is minus 1 over 2 times 1 minus the correlation coefficient squared. And then I have this ellipse. Okay, so I have x minus its mean squared over the variance of x, 2 correlation coefficient x minus its mean, y minus its mean over the product of the standard deviations, plus y minus its mean squared over the variance of y. Okay, so this whole thing inside is basically an ellipse. Okay, so it's kind of specifying an ellipse, and that's what we're going to see in these pictures, which we are going to go back to in just a moment. So the 5 parameters I need to specify this family are the mean of x, the mean of y, so those are mu x and mu y, the variance of x, sigma x squared, the variance of y, sigma y squared, and rho xy, the correlation coefficient of x and y. Okay, and if you remember back to the previous topic of covariance and correlation, you can get the correlation coefficient via the covariance. So if you had the covariance and the variances, you could get the correlation coefficient. But it's a little more compact to write this using the correlation coefficient. Maybe the most important thing I can tell you here is that you can connect these to the A, B, C, and D from the linear combinations before, but don't worry about that too much. So it's just important to know that there is a standard independent U and V underneath this, but we don't need to worry about exactly how to connect it. And in fact, we don't even need to worry about how to memorize or remember this formula if you're not using it that often. So it's okay to not remember it, and it is a little bit long, so it's fine to just forget it and look it up. But the intuition for what Gaussians are about is going to be important. So the one thing we should remember is that the joint PDF is fully specified. Okay, so joint PDF is fully specified by the parameters mu x, mu y, sigma x squared, sigma y squared, and rho xy. Okay, so if I have those 5 numbers, I've fully described the joint Gaussian distribution. And the nice thing about that, as we're going to see, is that as I'm going along and manipulating jointly Gaussian x and y, all I need to do is figure out how do the means, variances, and correlation coefficient get updated. I don't need to play with the joint PDF directly. We'll see more of that in a bit. And the vector-based expression for this joint PDF can be a little bit easier to remember, but again, this might be a little bit much at first, and I think it's better to just try to develop intuition for what these things do. But we're going to take a moment and just see what the vector-based expression looks like. Okay, what is it? Well, it's the same thing, so it's this formula I had before. It turns out I can write this normalization constant as 1 over 2 pi times the square root of the determinant of this thing here. And I'm going to say what this thing is here in a moment. And then I have x minus a half times this vector, which is x and y minus their means. Then I have this matrix that I had in this determinant, but now I'm going to take its inverse. And finally, I have the column vector of x and y minus their means. Okay, so this is a different way of writing what I have above. And it turns out that this thing inside is the covariance matrix, which we're going to see more about soon. Okay, so this thing that I can write inside, I can write x, y as a vector minus their mean vector, the inverse of the covariance matrix, x and y again minus their mean vector, and that's it. Okay, so this is the vector form. And in the next video, we're actually going to be talking about random vectors. So this might make more sense after you go and watch that video and come back, but it's here just to keep everything self-contained. So the notation is that this mu with the bar under it is the mean vector. So it contains the mean of x and the mean of y. And this kind of bold-faced sigma is the covariance matrix, which holds the variance of x and the variance of y in the top left and bottom right. And on the other two coordinates, I have the correlation coefficient times the standard deviation of x times the standard deviation of y. And that turns out to be the variance of x, the covariance xy, and the variance of y. So this actually turns out to be a little bit easier to remember in that the vector form of it is kind of more compact, and all you have to do is think about these two objects, the mean and the covariance matrix, or the mean vector and the covariance matrix. And those are replacing this mean and the variance from the scalar case. Okay, so that's the mean vector, that's the covariance matrix. Okay, so the main thing that I want you to know is that we're not expecting you to remember all of this stuff right away, but this is a more compact form, and eventually if you work with these more and more, this will be the one that you remember. Okay, and it generalizes immediately to more than two random variables, and that's why it's so important. So let's just try to build up some intuition for what this thing is going to look like by looking at the contour plots of this joint PDF for different choices of the parameters. Okay, so we're going to change the parameters mu x, mu y, sigma x, sigma y, and rho xy, and we're just going to see what happens to the contour plot. Okay, let's get started. So I'm going to have this big table. I'm going to have the mean of x, the mean of y, this variance of x, the variance of y, the correlation coefficient of xy, and I'm going to have, to start, just the standard independent Gaussian. So that turns out to have the parameters 0, 0, 1, 1, and 0. So that you could go and double check, is this standard independent Gaussian we had from the beginning? And its contour plot looked just like these kind of circular rings, right? And so what do we know about this? It's circularly symmetric, which is nice, and it is centered at the origin. Okay, so this is what we already recall from the beginning when we were looking at the independent standard Gaussians. So let's see how this changes as we alter one parameter at a time. So in this slide, we're going to just change the mean. So I'm going to move mu y to be -1, and otherwise I'm not going to change anything else. So what do I expect to happen? Well, the mean of y has gone down, so I expect the contour plot to go down. And that's what happens. So the contour plot is just going to go down. There it is. So it just shifted down a little bit, still circularly symmetric. Now it's centered at 0 and -1 because that's the coordinates of the means. And so the effect of this was just to shift it down by 1. Okay, so that's kind of the position of this. So let's do this again. Now I'm going to have x have mean 1, y have mean 2, keep everything else the same. And now I'm going to shift up and to the right. Okay, so again, it's going to be circularly symmetric. Now the center has moved to be the mean of x and the mean of y, which is now 1 and 2. Okay, so it shifted up to match that. And so it shifted right by 1 because of x, and it shifted up by 2 because of y. Let's do this again. So now what I'm going to do is just change the variance of x. So I'm going to change it from 1 to 2 and leave the means and the correlation coefficient the same and the variance of y the same. So what's going to happen is I'm going to get a stretched plot. So it's actually scaled by the standard deviation, which is √2 along the x-axis. So I've stretched it out by √2. It's still centered at the origin, which is nice, and because I've left the mean the same, and that's it. So now let's go ahead and do the same thing, leave x alone and stretch y now by 4. And I see that it's even more stretched, right? So now I've scaled it along the y-axis. So now I've scaled it by the standard deviation, which is the square root of the variance. So that's going to be 2 along the y-axis, right? And it's still centered at the origin. Okay, so we've played with the means, we've played with the variances, and let's play with the correlation coefficient. So we're going to leave everything the same, and now I'm just going to adjust the correlation coefficient to 1/2 or 0.5. And I get something that is now going to be stretched along the y equals x line. So I've kind of pulled it along into this y equals x line, and it's still centered at the origin. Okay, so why is that happening? Because when the correlation coefficient is positive, it means that as it goes towards 1, x and y tend to have more of a linear relationship, right? So they're better approximated by a line. This first circle is not well approximated by the line y equals x, because I could have picked any line, y equals minus x. All of those lines would have the same effect, whereas here the line y equals x is actually a very good fit. And I can make it better by making rho xy higher, so let's say 0.9, and I can see this starts to resemble a line more and more. So it's stretched even more along the y equals x line. And in fact, this would continue all the way until I made rho xy equal to exactly 1, and then would collapse down to a line. Okay, so that's basically what's going on. It's saying that with this rho xy, I can determine how much of a linear relationship exists between x and y. All right, so let's start to play around with some of these parameters together. Okay, so now what I'm going to do is I'm going to first try making a minus 0.5, so I can see that now it's going to be stretched along y equals minus x, as we were predicting, and it's still centered at the origin. Okay, so the next thing I'm going to do is just hold on to this, let's say minus 0.5, and now I'm going to also scale x's variance, okay? So I now set the variance of x to 4, and I see that now it's kind of stretched. So it's stretched, and it has a negative slope, right? Because of the correlation coefficient, and it's scaled along the x-axis. So there are two things that have happened. Because of the correlation coefficient, I now see that it's kind of, has a little bit of a linear relationship, and it's also stretched out along the x-axis because of this variance. Still centered at the origin. Okay, one more set of plots. Let's move the mean. Let's change the variance of x to 2. So, and here, by the way, let's try to predict what's going to happen. So I made the mean of x 2 and the mean of y 1. And so I now expect it to be centered at 2, 1. So now I'm going to make the variance 2 and the variance of y 1. So what do I expect the effect of that to be? I expect that the x-axis will get scaled because I've changed it from 1 to 2. Okay, so we're trying to make these predictions before we see the plot. And now I set the correlation coefficient to 0.5. So I expect it to be stretched with some kind of positive slope along some kind of line, a positive slope line. And let's see what happens. That's exactly what I get. Okay, so I see something that's centered at 2, 1. It's more scaled along the x-axis than the y, and it's stretched along a line of positive slope. One more attempt. Let's do 0.5 and minus 0.5. And then that means that it's going to be centered at 0.5 and minus 0.5. And it's going to be scaled along the y-axis because I've changed the variance of y from 1 to 4. Right? So it's going to be even more scaled than what I saw before when I just changed the variance of x to 2. And I have a very negative correlation coefficient, so it's going to be quite stretched with negative slope. And let's see if we get something like that. So indeed, we get something that is centered at 0.5 and minus 0.5, and it is is well approximated by a line. Okay, let's talk about some properties of jointly Gaussian random variables x and y. All right. The most important thing to keep in mind is that a linear function, maybe plus a constant, of x and y is going to be Gaussian. Okay, so if z is equal to alpha x plus beta y plus gamma, then z itself is Gaussian with mean mu z and variance sigma z squared. Mu z is, I just get by linearity of expectation. So I just have alpha times the mean of x plus beta times the mean of y plus the offset gamma. And the variance I get using the formula I developed in the previous video. So it's going to be alpha squared times the variance of x plus beta squared times the variance of y plus 2 alpha beta times the correlation coefficient times the standard deviations, which is the covariance xy. Okay, so you can go back and see that that's true. This is a super important property because what it means is that I only need to track the means variances, and covariances under linear transformations, or the correlation coefficients. Okay, so instead of having to work out what happens to the PDF under every linear transformation, all I need to do is just use linearity of expectation and variance of a linear function to keep track of what happens to all of these different terms, right? And that's a lot easier than doing these PDF transformations. The other thing that I know is that the marginal PDFs of x and y are going to be Gaussian, and they're going to have the parameters from the family. So mu x, sigma x squared, and y is Gaussian, mu y, sigma y squared. And also, if w and z are both linear functions of some jointly Gaussian x and y, maybe plus some constants, then w and z themselves will be jointly Gaussian. Okay, and the reason this is true is that the definition of a jointly Gaussian random variable pair is that it's a linear function of some independent standard Gaussians. And a linear function of a linear function is itself a linear function. So then I get that it's also a linear function of independent standard Gaussians. Okay, more properties. Uncorrelatedness for jointly Gaussian random variables is equivalent to independence. This is not true in general, but it is true for jointly Gaussian random variables. And the correlation coefficient is exactly equal to 1 if and only if x is a deterministic linear function of y and vice versa. Okay, so I only hit this absolute value of 1 when one is a deterministic function of the other. And in fact, then they would both be linear functions of one another. And I also have that the conditional PDF of x given y has a simple form. It's also Gaussian. Okay, so I don't need to do any work to get the conditional PDF of x given y, or of y given x. I could just flip it around. And the mean and variance in that case, I just get with these formulas, and we're not going to derive why these are true. These are just things you can look up in your lecture notes. But this first formula that I have is that the mean of x given y is going to be mu x plus rho xy times the standard deviation of x divided by the standard deviation of y minus its mean. Okay, so think about what it's doing is it's trying to adjust the mean of y by taking away y's mean and adding in x's mean. And then it's rescaling y to be on the same scale as x by dividing by the standard deviation of y and multiplying by the standard deviation of x. And it's finally trying to capture how much of the linear relationship exists with this correlation coefficient. An alternative way to write the exact same formula is just to replace the correlation coefficient and standard deviations with covariance xy over variance xy. So both of those are useful, just depends on what you're given. The variance given y is going to be 1 minus the correlation coefficient squared times the variance of x, or the variance of x minus the covariance squared over the variance of y. All of this is really important for estimating things, and we're going to see more of that later. Okay, so these formulas maybe don't play so much of a role for us right now, but we're going to see why they're so important very soon. Let's do an example. In this example, which I'm going to track for a little while, x and y are going to be jointly Gaussian. Okay, and in order to specify jointly Gaussian random variables, I don't need to write down the joint PDF. I can just tell you the parameters. Okay, so there are 5 parameters that I have to tell you for this pair. I need to tell you the mean of x, that's going to be 3. I need to tell you the mean of y, that's going to be minus 1. The variance of x, that's going to be 4. The variance of y, that's going to be 1. And the correlation coefficient here I'm going to take to be minus a 4th. Okay, and I'm going to say that w and z are indeed linear functions of x and y. W is x minus 4y plus 1. Z is 2x plus 4y. Okay, so the first thing that we can recognize is that since w and z are linear functions of jointly Gaussian random variables, w and z are also jointly Gaussian. So then to characterize w and z, I need to find their means, variances, and correlation coefficient. And that's what I'm going to set out to do. Let's first determine their means. Okay, and these are all going to rely on properties and tricks that we've learned before. So to get the means, all I need to do is recognize that I can use the linearity of expectation. So I'm just going to remind you of that property, which we've seen many times. In this case, it would correspond to the expectation of ax plus by plus, let's say, e is going to be equal to A times mu x plus B times mu y plus E. Okay? So that means that mu w is the expectation of x minus 4y plus 1. So that's going to wind up to be 1 times mu x plus minus 4 times mu y plus 1 using that formula. And so I just plug in these parameters. I get 1 times 3 plus minus 4 times minus 1 plus 1, and that's going to be 8. Same thing for mu z. The expected value is 2x plus 4y. That's going to be 2 times the mean of x plus 4 times the mean of y. That's going to be 2 times 3 plus 4 times minus 1, and that's going to be 2. Okay, on to the variances. The variance of a linear function is a little different. I can't directly use the linearity of expectation because the variance has these square terms, but we already have a formula for the variance of a linear function. And the only thing to remember here is that it's in terms of the variances and covariances, okay? So the variance of ax plus by plus e is equal to a squared times the variance of x plus b squared times the variance of y plus 2ab times the correlation coefficient times the standard deviation of x times the standard deviation of y. And this whole thing is actually just the covariance of x, y. Okay, so you could just replace this product of three things with the covariance x, y. All right, so let's work this out. So that means that the variance of w is just going to be the variance of x minus 4y plus 1. That's going to be 1 squared times the variance of x plus minus 4 squared times the variance of y plus 2 times times 1 times minus 4 times correlation coefficient times the standard deviations. That's going to be 1 times 4 plus 16 times 1 minus 8 times minus 1/4 times 2 times 1, and that works out to be 24. We'll repeat the same thing for the variance of z. That's going to be the variance of 2x plus 4y, which is going to be 2 squared times the variance of x plus 4 squared times the variance of y plus 2 times 2 times 4 times the correlation coefficient times the standard deviation of x times the standard deviation of y. And so that's going to be 4 times 4 plus 16 times 1 plus 16 times negative 1/4 plus 2 times 1. And that again is going to be 24. So I actually just chose this example. So these both work out to be 24. Okay, so, all right, so those are both 24. And now what we need to do is just move on to work out we're just backing up a bit. And that's also going to be 24. Okay, so what we just showed was the mean of w is 8, the mean of z is 2, the variances of w and z are 24. Okay, so the last thing to do is to determine the correlation coefficient, right? So if you look on the right here, we have the top 4 parameters now for w and z. We need the last one, the correlation coefficient between w and z. Okay, so remember that the correlation coefficient is defined as the covariance of w and z divided by the standard deviation of w and z. All right, so let's just calculate the covariance. And we've already seen a formula for computing covariance of linear functions, and we're just going to employ that directly. Okay, so the covariance of two linear functions, so ax plus by plus e and cx plus dy plus f, we know that that's going to be ac times the variance of x plus ad plus bc times the correlation coefficient times the standard deviation of x times the standard deviation of y plus bd times the variance of y. Okay, and that covariance of wz is therefore the covariance of x minus 4y plus 1 and 2x plus 4y. So I can just read off these parameters. It's going to be 1 times 2 for AC. And then for AD, it's going to be 1 times 4. And then for BD, it's minus 4 times 2, sorry, BC. And then I'm going to get correlation coefficient times the standard deviations. And then plus minus 4 times 4 for BD times the variance of y. Okay, so plugging in what we know, I get 2 times 4 minus 4 times minus 1/4 times 2 times 1 minus 16 times 1, and that's minus 6, which is fine. It can be negative, and that means that the correlation coefficient is minus 6 over square root 24 times square root 24, which is minus 6 over 24, which is going to be minus 1/4. Okay, so in this particular case, it turns out that the means changed and the variances changed, but the correlation coefficient stayed the same. And that is just sort of a coincidence of the example design on my part. Okay, let's do a little bit more. So what we just showed are now also we also showed the correlation coefficient is negative 1/4. So what is the conditional PDF of W given that Z takes on a particular value? Okay, so let's see how to deal with this, right? So this is an object that we're going to be seeing more of later on. So let's actually practice dealing with this. Okay, so the conditional PDF is going to be Gaussian with mean that corresponds to the conditional expectation of W given Z. And we know from above that that's going to be W, mean of W plus the correlation coefficient times standard deviation ratio times Z minus its mean. Okay, so this is a formula we had just on a previous slide, and we also had a formula for the variance of this conditional PDF when both W and Z are jointly Gaussian. And so the variance of W given Z was going to be 1 minus the correlation coefficient squared times the variance squared of W. Okay, so let's just work out these formulas. So this first one's going to be 8 times plus negative 1/4 times root 24 over root 24, Z minus 2. That all works out to just be minus Z over 4 plus 17 over 2. Okay, so what that means is that if I'm trying to predict if I'm trying to figure out the average value of W after observing Z, I take Z, I multiply it by minus 1/4, and that makes sense because that's the correlation coefficient, which tells me how they're linearly related. So it makes sense that it's capturing this slope, okay? Especially since their variances are the same, so there's no need to rescale Z in terms of W. And then I just need to deal with a mean offset, which I did with 17 over 2. Okay, for the variance, I'm going to again plug into this formula, conditional variance. I'm going to get 1 minus 1/4 squared times 24, and that's going to be 15 over 16 times 24 is equal to 45 over 2. Okay, and so finally W, given that Z is equal to little z, is going to be a Gaussian random variable with conditional mean, which is minus Z over 4 plus 17 over 2, and conditional variance, which is just 45 over 2. Okay, that's great. And finally, now we can just ask this conditional probability question. So given that Z takes the value 6, what is the probability that, let's say, W stays less than the value 7? Okay, so I know that Z is 6. What's the probability that W is less than 7? So I can write this as a conditional probability question. The event that W is less than 7, given the event that Z is equal to 6, that's going to be the phi function, right? So this is because this is using the fact that I'm dealing with a Gaussian, even though I have a conditional PDF. So I'm going to use the phi function for what I'm interested in, and I'm plugging in the conditional mean, okay? So minus Z over 4 plus 17 over 2, and Z here happens to be 6. And the way that I use this phi function, remember, is I'm just plugging in the thing I'm interested in, 7, minus the mean, in this case, the conditional mean, divided by the variance, in this case, the conditional variance, or rather it's square root. So I have square root of 45 over 2. This all simplifies. And okay, so just to emphasize, the reason I can do this is W given Z is Gaussian. And the reason this all simplifies to just be phi of 7 minus 7, again, just by my choice of parameters. And then this whole thing is just going to be phi of 0. And so we don't need to reach for a calculator. Phi of 0 by symmetry is just going to be 1/2. Okay, so that was just a quick walkthrough of how I can actually deal with what might seem like a rather complicated joint PDF. That's the joint PDF of a jointly Gaussian random variable. I see that if I want to do calculations, I can just get by tracking parameters. And then when it comes to calculated probability, then I can reach for the phi function. But I never really need to integrate directly on the joint PDF.